Thank you, Suzanne. So good day, everyone. My name is Sophie Trentafilidou, and I am the IS&T Vice President for Conferences and organizer of the Best Student Research Seminar Series. On behalf of IS&T, the host of this program, it is a pleasure to welcome you all today here. Before we begin with the seminar, I would like to take a moment to tell you about IS&T. The Society for Imaging Science and Technology brings together researchers and practitioners in industry, academia, government, and cultural heritage from across the globe, and its aim is to advance imaging across applications from capture through image processing to display and output. IS&T's dedication to creating welcoming spaces for colleagues from industry and academia makes it a unique space, especially for students trying to learn more about professional opportunities and resources, and it's good to have so many students around today. So IS&T offers a number of conferences and publications to showcase the work that's happening around imaging. For those who don't know it, next year is the 25th anniversary of IS&T. For nearly 30 years, IS&T has brought color scientists together on research in the field to debate standards on color and search experiences with the CIC conference. Our technologies advance from printed product to display to XR. CIC has evolved, the Color Imaging Conference has evolved to meet the needs of students and practitioners. CIC 29 takes place this year next month, November 1 to 4, with short courses offered the 2 weeks before the technical program. We encourage you to look at the program. Besides traditional keynotes, talks, and posters, CIC also offers a series of workshops and online activities designed for discussion and exchange. Another event that may be of interest for those who don't know is the Electronic Imaging Symposium, which offers a breadth of topics from sensors to image quality to XR and automotive, and many more applications. Excuse me, something went wrong with my slides. Okay, so finally, before we start today's program, I want to remind you that there are 2 more student seminars in this year's series taking place in the coming few weeks. And now it's turned to today's program. Today's speaker is Jiang, who won the CIC 21 Cactus Award for Best Interactive Poster Paper for Effect of Peak Luminance on Perceptual Color Gamut Volume. Fu received his PhD this past March from RIT's Munsell Color Science Laboratory and is currently a display metrology engineer at Apple. After Fu's presentation, we will open the floor for discussion, but I leave now the floor to Fu. I stop sharing my slides. Welcome, Fu, and to you.
All right. Thanks for this introduction, Sophie, and thanks everyone for attending. Let me just put my slide here. All right, so is my presentation looks okay to your side?
Yes, it's all good.
All right, thank you. So thanks everyone for coming. Today I will talk about my work. One of my projects working in during my PhD is the effect of peak luminance on perceptual color gamut volume. So it's a work from me, Mark Fairchild, who is my supervisor from IIT, and the Kenichiro Masakosa, who is from NHK Research Center. So before we jump into the talk about a little bit about myself, is I finished the PhD in March from Munsell Color Science Laboratory in IIT, and my PhD work focused on the HDR display perception from like 4 aspects. The first is color gamut volume, both computational and perceptual, which like we're going to talk about on the second part today. Then we say perfect black on display and perceptual diffuse white on HDR display, and the simultaneous dynamic range. Then the last part actually is going to CIC this year. I think I'll go to present the work as well. Then currently I'm working as a display metrology engineer in Apple. So that's a bit about myself before we jump into like the talk, and also, I mean, provide some information. If you're interested in any of my PhD work, we can also discuss after this talk. All right, let's dive into today's topic. So everyone knows display and TVs, like they're in industry being saying using some metric to present their ability of color reproduction. You can see on the left part image is a chromaticity coverage diagram. You can say, okay, the display has the coverage of Rec 709 or sRGB standard, or Rec 2020 or DCI-P3, or sometimes people say it's like 75% of the DCI-P3, something like that. So they use that as a metric to represent how the TV's color reproduction capability. But also you can see on some of their promotions, or they were saying just color, just say we have 16.7 million colors, but it's just equally saying this is a 8-bit RGB display. Or say it's like 1 billion, which is just like a 10-bit RGB display. So all those metrics actually, it's like maybe it's easier to understanding for the customers, but actually it's not that sufficient or effective as color science would say. So there was some computational color gamut volume, which is proposed saying, and I think also there's a CIE just proposed a standard definition maybe last year. So this is usually defined as a mathematical volume in 3D color appearance space. I think mostly people will calculate this in a C-lab space. So we present this, present this work in maybe a few years back in CIC as well. So we had a paper called Estimation of HDR White Color Gamut Display Color Gamut Volume. That we have a model to calculate or easily saying compute the mathematical or say computational 3D volume in color appearance space. You can see on the right side, this formula is just saying the predicted volume is you have 3 factors and 1 constant. The 3 factor will say is some polynomial relationship with XY chromaticity, area coverage, peak lumens, and your display RGB configurations. So it's a simple about the computational color gamut volume. If you're interested in more detail, you can check out the paper. We are not going to dive too much here, but the problem will be how this computational 3D color gamut volume correlates with our perception. So that's like actually drive us to do such to like have such a research after our first publication, the talk in CIC about the computational one. So what is done here? So we did 2 psychophysical experiments exploring the peak luminance effect on perceptual color gamut volume. Then we do some correlation analysis saying, what does that have good correlation with this computational 3D volume or other matrices? Then we find some actually fundamental difference between the perceptual color gamut volume and the computational one. Also, I mean, saying the definition and all the how exactly we should evaluate the perceptual color gamut volume. So the experiment setup is saying on this left side, the image is showing this the top view, like image of how the experiment set up. We use a Sony TriMaster OLED display, which have a capability of full screen 1000 nits, like stable one, which is used as usually as a reference display. It's a professional one, and which is we borrow from NHK, thanks to Kanichira. Then we have observers sitting in front, and it was a dark area. So we, in these experiments, you can see in the bottom part, it's the experiment flow. We use a pair comparison. So we show one image, then for like 15 seconds, then on the dark image, we show 10 seconds, and then the second image for 15 seconds. Then the observer need to make a decision saying which image is more colorful and detailed. So you can see this is our definition of color gamut volume is saying the same image, if they're the same image, original image raw data is showing on two different, or you say to have some difference, then how we define which one have more color gamut volume. And the reason we're doing such a pair comparison, like in this, it's like sequence one, is because we want to mimic the situation saying, when you adapt to your own display at home, then you go to a friend's or a store, you see another display. How does that difference? Instead of side by side, because if you do side by side, it's more like saying you go into a retail, like a store to see or compare all of them side by side, because people actually, that probably will exaggerate the difference because we will adapt as everyone knows, right? So as for observers, for experiments, we have two experiments, right? So experiment 1, we have 21. Experiment 2, we have only 20. I think someone was not happy with first one. Then for the ages from 20s to 60s. And I think the majority of them are from the lab, actually, from Munsell Color Science Lab. We have faculty and all the students as well, and some of the other people. So a little bit about the experiment detail. So the experiment method is for the two experiments, they're the same, both pair comparison and observer number. So, but the key difference well here is the imaging processing method. So the imaging processing method means we want to explore the effect of the peak luminance, right? So we saying, okay, we want to simulate how the display with different peak luminance will process the same raw image data. There's two types. One is hard clip, saying if everything is above, we just do a clip. And the other is a scaling, right? So if you have 1,000 peak, but our display is capable only of 500, then we scale everything. That's a luminance scale. And in terms of that part in the experiments, actually we use the ND filter in front. So we show in this exactly the same image, but we put a ND filter in front of the display. But for the peak luminance hard clip, it's digitally, like we clip that data and we showing on the display. Here I have two examples. So you can see from the left side is example of a clipping. So from the top left to the bottom right, the peak luminance capability is increasing. So you can see the light in the red box is becoming like clear and like more sharp, more detail there. And on the right side is an example of scaling. So also you can see from the top left to the bottom right, it's increasing. Or we say that the peak luminance is like increasing as well. I mean, the actual image will not showing like this dark, especially for the scaling part on the top left one, because it's the actual one is still around 200 or 300. This is just a illustration. So then for the experiments images, we have totally we have 9 original image. We're trying to balance between imaging numbers and like the experiments time as well. So we totally have 9. We have all different types. We have people, we have like inside and the outside as well, have brighter and the dark ones as well. Then each of the original image will process through two different ones. So the clipping wall, the peak lumens were simulating to clip to 1,000, 500, 300, and 200. And with the filters, that wall goes with 1,000, which is original, and 700, 500, and 350. So each original image will generate 4 different images, which will have 6 pairs. So in total is a 54 comparison of each experiments. Okay, let's go to the experiment results here. So so we do the experiments when we follow the analysis with the angle drop, the paper, the book, that the analysis, how that works. And then we say, okay, the vertical axis is a perceptual color gamut volume. The horizontal axis is a peak lumens. On the left, it's on a linear scale, like the peak lumens. And on the right side, it's in log scale. So then the red line is experiment 1, which is the clipping. The blue line is experiment 2, which is scaling. So you can see, like obviously they have a better correlate. The perceptual color gamut volume have a better correlation in log scale rather than linear scale. But from our if you remember from at the beginning, I introduced our computational 3D volume, which actually is showing it has a better correlation in the linear scale instead of log scale. So that's like the mismatch, say, or the disagreement between the two, between the computational color gamut volume and the perceptual color gamut volume. Another interesting thing you can see is the slope of the linear of the 2 experiments. You can see clearly it's more steep for experiments 2 than experiments 1, because you remember experiment 1 is doing a hard clipping, which will just blurring a little bit of the detail, but the observer probably will not notice at all. But experiment 2 is like doing the scaling, so they were saying, okay, oh yes, it's being more colorful, especially. So that brings us to the question: what will better correlate with our experiments results? So here we have a table of the correlation analysis. Is R² between the experiments and the different matrices. So on the first column is all different matrices. You can see it's a peak lumens or the log scale of the peak lumens, then LCH, JCH, QMH, and the peak Q. Here I'll explain a little bit more. So LCH means the 3D color gamut volume with the settings of the peak lumens in LCH, or you can say C-Lab color space, and JCH means the 3D volume in JCH color space, and the QMH as well. The peak Q here means it's a peak brightness. So I have the green box here showing the best 3 correlation matrices with our experiments. You can see it's either peak brightness, the log scale of the peak brightness, or the log scale of the QMH, or the log scale of the peak lumens. And the peak lumens itself, the linear one, actually it's like not that bad, but it's not the best one. And also it was predict should have the best correlation with the from the computational color gamut volume. So that's kind of interesting why there is such a disagreement. So we have explanation or hypothesis here is, so the difference here is okay, so when you show an image, you're not going to use the whole display's color, the color reproduction capability. You can see I illustrate the example here. the image here. So on the image, there are two black axes on the bottom, which is representing the chromatic axis, and the vertical is like the achromatic axis. You can see usually in when you show a real picture image, it will most of the part you're using is below some level, below some like you say luminance level or brightness level. Then only some of the like the very bright like direct lighting or like the specular part while using the very bright area. So it's not using equally. That's like showing the difference between your computational volume, because in computational volume you are assuming everything is in color appearance space, you are assuming they're equally used. But when you do the experiments, you always show image instead of, you cannot say, okay, we just display all the possible the colors in there. So that's like the difference. So when you do in our two experiments, when you do the scanning or you do the clipping, you are not affecting the whole the image. You are affecting part of the image. Especially when you do the clipping, you are only clipping the specular part or the direct lighting, which have like a high brightness, chromatic area. So that's like saying that's the key difference between your computational volume and how you access the perceptual volume. That's why we're saying it's like we will actually at the end of the experiment, we probably will suggest to use a different matrix when you want to evaluate or to present the display's color reproduction capability. So I hope this the simple illustration here will work, will like help to understand our hypothesis here. All right, then the conclusions and the future work is like the first is like saying the perceptual color gamut volume is showing the difference from the computational 3D volume. Obviously, as we shown before in both the result and also the correlation analysis. And the difference is like fundamental. As I just explained, the difference is between, you can say it's between a theory and the practical usage of the display. So that's what suggests us to use different color gamut volume for different purpose. And also, I mean, that brings us to another question is how would you define a perceptual color gamut volume? So there's no clear definition so far. So that's kind of then for the future work actually is in terms of the experiments itself, maybe more images can be used. And also here we only have two types of imaging processing style. One is hard clipping, then the other is scaling. Maybe you want soft clipping and maybe tone mapping, which probably will optimize your TV's capability in terms of showing the HDR or like this, mostly like HDR images. And also here we only explore the effect of the peak luminance level, but also you say the primary, for example, if you have a piece, this DIC P3 display, then you can simulate how it looks like to sRGB and the effect of that. And also probably the joint effect of the chromatic area coverage and peak luminance for a comprehensive understanding of perceptual color gamut volume. I mean, also with all those data, you can probably will build up a model to predict or better represent the perceptual color gamut volume. Yeah, as the last point is like also is really important is the perceptual color gamut volume still lacks the clear definition. I think the reason here is it will maybe depends on your purpose. For example, here we saying is more detailed and colorful. maybe if you want to, if you have a special application, you probably want a clear definition about that part as well. For example, if you're exploring the darkness of your display, then you probably want to show, okay, which is more like no artifacts, more like the change is more smooth and all the stuff when it's showing some of the specific like dark patterns. Yeah, so that's kind of like a whole, so in terms of perceptual color gamming, our work is maybe just a start, but it have a lot of directions you can go and to explore as well. All right, I think that's the end of my talk. Thanks everyone for coming.
Thank you, Fu, very much for your presentation. And again, congratulations for getting an award for the paper. You can stop sharing the screen now, and we can see you. Maybe actually, okay, if we need to bring the slides up, if somebody has a question, we can do it again. And I would like to open the floor, and I think there are already some people. No, there are people who are congratulating you. So I would like to open the floor to see if anyone has a question for Fu. If you do, either raise your hand or put your camera on directly, and you can. We have more applauding for you, Fu.
Oh, thanks.
So while people are thinking of possible questions, I have a couple myself. First, regarding your experiment, which essentially you flip between images with a black screen in between, and I have been doing similar experiments, and I guess there are advantages and disadvantages to having two images, the one after the other, or together, obviously. One obvious is that you have different luminances and adaptation, but I was just wondering about, there is some kind of memory effect, isn't it? Because so, and also I was wondering why you put black in between, because then you vary luminances falling on the retina instead of a kind of mid-gray, or, and if this has any effect. And the other question, again on the same topic, is whether there are after images, so whether the 2 seconds that you leave in between, and if this has an effect, an actual effect. But as I said, these are questions that I have for my own experiments. I tend to put a mid-screen luminance so that I don't have great adaptation.
Right. Yeah, so I think it's not a absolute black level there. I think it's just really low. Another thing is we put like 10 seconds in between. As we said, is actually we do not want them to adapt to a specific level. We want to then adapt to the image itself. So in between image, we do not want to say, okay, you adapt to some certain grade to like for some time, then that will probably affect your adaptation to the second image. Right. So because our purpose is to compare with different situation when we were saying is you already adapt to. So yeah, but it's a good question, because actually for the timing and the stuff, for the after image and the memory effects, we did some pilot study to make sure in terms of the experiments. A key part is the experiment's timing, how long it takes. We do not want to then to be.
No, I, as I said, I have the same questions, and I have done, similar experiments, and I have ended up with similar type of settings, but it was just your take to that. Scott, you have raised your hand. Do you want to put your mic on, and if you want your camera too?
Sure. Yeah, I'm barely awake. Pacific Coast time here, but
not forcing you.
Enjoyed the talk. Look forward to reading the paper in more detail. One issue in this entire topic area is you have people have to make assumptions about the images themselves, and we don't really have a good model of image statistics. So like there was a brief mention of what are you adapted to. And when you consider, watching video, maybe large screen cinema, over the course of, thousands and thousands of hours of watching, are certain, images going to appear. Sometimes people say, well, we don't want to consider the entire range of adaptation. It's not practical. But when people use the term practical, there's no numbers. So then it's kind of a question of handling all cases, kind of a worst case engineering approach, or some arbitrary definition of what's practical. And kind of as an example, where you really start pushing the unusual cases, you could say, where you could say it's impractical imagery, often is in the world of art. A really good example is Ad Reinhardt. He did a series of paintings called 9 Paintings. They're all black when you first look at them, but they're consisting of different colors when you watch long enough. These are in the San Francisco Museum by the coast, if you ever get a chance to go there. So then the question is, okay, well, that's an impractical image, so let's not worry about that. But then it's kind of a sad state that you're kind of ruling out art from the beginning when you make those kind of statements.
Absolutely.
So yeah, just kind of a big philosophical point on sort of worst case engineering, and when people start bringing up the term practical in terms of imagery. Thanks.
Yeah.
Thank you, Scott. Point taken very much, and I'm in the same line of thought very much regarding what do we do with the outliers and how important are the outliers, and we have been tending to excluding them as engineers, but when are we going to encompass them? Go ahead. The question is for you anyway.
Yes, so thanks for the question. It's a good question. So because we saw this one is for more like general case and also for static image, as you mentioned, for if you're watching videos or like that will be totally different. You probably were not able to adapt that faster, right? You're always like in some level. That's why I think from Dolby Vision, someone showed an example in this in one of the CIC, which is really interesting. It's like how those high dynamic range can help you to like dive into the experiments when you're watching a movie. It's like when someone in the cave adapting long enough into the dark area, but when you walk out of the cave, the sun is so bright with like high dynamic range image, you can make the audience or the people to experience that situation like cyclically, because you feel that bright and all the stuff. But for you say in the corner case, I would say our work is definitely not for that corner case, or say, for example, you say the very dark ones. Then for that specific one, I will agree saying we probably need some specific work to showing saying, okay, that's like different. But for the general understanding of how displays color reproduction, that's our target of this talk. I mean, as actually in my one part of my PhD work is the perfect black of display, which is showing like really dark image. Then we showing to what level to what black level the display will be sufficient, even when the area is really dark and it's very little scattering in your vision system. So it's really close to your limitation. Then we have some model actually work there. That will be explained to your questions. Like, for example, when you say, look at really dark area and you look for like long enough, then you will see, okay, our display on that situation, you should have different matrix, especially for like the dark area, because that's the kind of situation is when your display is really dim, your whole environment, then the whole movie has to be really dark in order to bring the people to that level, right?
Yeah, I guess I have another question since my camera's on. So the log 10 of luminance is kind of interesting and convenient. Have you thought about how much your work or your finding connects with the CSF as a function of light adaptation? So for that, the CSF, once you get into the 300 candelas per square meter range, then it does become logarithmic for all frequencies. So it seems like your work supports some findings in the CS that we see in the CSF as well.
Right. Actually, that's a good point. We haven't seen that to go in that direction yet. So, but it's interesting because our explanation here is more saying when, especially when you do the clipping and okay, let me split it into the two experiments. The first one is a hard clipping. So as we explained, when you do a hard clipping, it's more like saying you probably will blur in some of the detail, you lost some of the texture in the brighter area. So that's come to our explanation. That's kind of like only small part of the image. So you're clipping, the effect is only those specular area or like direct lighting, like the colorful lighting. So that's kind of saying, okay, when you do the clipping, it's more that area. Then it's like a linear instead of a 3D volume. It's a linear part. Then that will explain because our perception in the brighter area is more linear. It's more linear to the log scale of the absolute luminance level. That will explain. Then for the second part, actually, for the scaling, most of the experiments, most observer feedback is saying, okay, they make their decisions based on more like colorfulness because you are doing scaling. You do not lose too much. That's why actually a good point is that we use an ND filter to make sure we are not losing any detail because the digital scaling. So like that actually corresponding with the Horner effect, the colorfulness is like increasing with your brightness. So then your log scale of the peak luminance is like close to your brightness scale, I would say.
Yeah, okay, thanks.
Yeah. Thank you, Scott. Any more questions? I'll throw another one, and it's in some ways in the same line regarding the detail. How did you feel? In some ways, you are looking at two different attributes. You're looking at perceived luminance and detail at the same time. Mm-hmm. Why did you feel that you have to put them together somehow? I know that the luminance would affect both, but in a way, if you were asking about the one only, would you expect different results, different responses? And how do you think the detail? You explain why about the clipping and the clipping will, but do you think you would have different results if you were just asking not about the detail and just about the perceived?
Right. I think it probably will have some difference because especially for the clipping one, you can see the clipping will mostly affect the details. If you just ask in the colorfulness, they probably get lost.
But then the modeling or your responses are a little bit, mixed. They're affected by and you don't know how much is affected. And did you have any discussions with your observers how much the detail part affected their overall judgment?
Right, that's a good question. For the first experiments, which is a clipping, they were saying they would just notice, okay, there is some loss of the detail, and also.
But how much did it weight, and okay, how much is it's obviously you can't quantify it.
Right. So they were saying it's more onto a little bit onto the details, but they also some of them also saying, okay, we based on some colorfulness, their scale, and also I think it's really. Sometimes it's not that easy to have just a single definition, say, okay, it either be colorful or detail. But I would say it may make that the results difference more subtle because it may slip away because
I would think so too. So in some ways you are, and this is where the CSF comes as well at higher luminances. Yeah.
Right. But I think the trend will be the same for sure. But the result maybe I'm not that saying 100%, but I say it may be still similar.
Yeah, your computational model doesn't take into account the detail. It's based on luminances only.
Right. Because it's like as you say, it's in color apparent space. So it's like it is actually already being in lightness, but it's in the 3D volume instead of like. That's kind of like bring back to the question is like how would you as long as you are assessing the perceptual color gamma volume, you're using images, which is not
Which is not
seeing the whole
flat
world.
fields. Yeah, no, absolutely. It's interesting. So
I think
we have John. John, did you put your camera on because you have a question?
Yeah, I have a question. If it's all right, or Susan,
Of
do you want
course,
to go
absolutely.
first?
Go ahead. Very welcome.
My question was just since he
Sounds-
just talked about the images versus flat fields, was just around the differences he saw with his different images and what he would think might happen if he used a different set of images.
Right. That's kind of a good question. It's like one of the future work. Because here we only have, we trying to include more, and we have all different types of images as I showed before. But of course, the more the better. And the thing will be, if that's kind of interesting. It's like also, as I said, if you were looking for the one specific application, you can just show a bunch of different no luminance level ones as the example as well, right? So that's kind of like another I would say if you're using more images and it's just general like image, I would say your result could be similar, because it's the difference between your I would say your perceptual the color gamut volume experiments will be fundamental difference from your computational one. That's there. But if you're using some specific types of image, I would say it may be different. If you're just using all the brighter ones, like ones like maybe a little bit overexposure or something like that, then all you need
also local salient areas in images that may attract the attention more or less, isn't it? It's not only the overall luminance, but it's structured so much in local luminances that might affect preference, isn't it? So it becomes complicated as soon as you put images in and not flat fields.
Right. Yeah, and the NASA image actually in the experiments, if you remember, it was just a bunch of trees in the building, which doesn't have a key at all. And for that image, even if you do a little bit like clipping and stuff, it didn't show much difference. So the z-score, I would say, from the observer is just flat. They didn't see any difference. They do not have their attention, and even there's some loss of the detail, they didn't notice that at all.
Right. Thank you, John. You were cut in some ways. Please
my question follows up your recent comment. First of all, thank you for a very interesting talk. I was curious as to what the clipped images looked like, because we all know what happens if you put a neutral filter in front of your eye. We had that experience, but depending upon what values in 3 space, in RGB space, the clipping affected, did it change things? Did it change any of the color appearances of any of the areas in the scene? And it's hard for me to visualize what that particular clipping algorithm did on that particular display. Can you speak to that?
Oh yeah. So for the clipping, it's a hard clip. So it's a digitally processed. So it's simulating, say, if you have a display of 500 peak lumens, then you have the primary, like in corresponding luminance level. Then you have the image. If you go there, it will just get clipped.
Did you verify that with radiometric measurements? Because I never trust what happens in all these displays.
That was digitally processed in the image. It's not it's not a processed by the display. It's
but we don't see digits. We see light.
It's processed by the
No, I understand the operation, but I don't understand what the observer saw or what it did to the display luminances.
Here. Let me show you here. I think maybe it was a quick, I lost. So can you see here? Do you need to see me? So on the example of clipping, you can see here on the left side.
Yep.
Let me just zoom in. So you can see here on the red box, you can see it's becoming more clear and more sharp, more brighter and more sharp. That's how the observer see, oh, the clipping is affecting, oh, it's getting blurry when it's below some level.
But an example, that light was a red light, and you clipped the red maxima, that would cause a color shift in the appearance of the rest of the image.
Oh, right. The image 5, actually, it will make the direct light more blurry.
Will not change that color?
It actually, I don't think it changed the color.
Okay.
It may be a little bit huge shift, but in digitally, because we are not just clipping the luminance level, we are simulating, okay, if you have the clipping on primary as well, the corresponding primary.
Thank you.
Yeah.
Thank you, John. Thank you, Fu, for your reply. Do we have any more questions from our audience? So in which case, if we don't have more, I would like to thank once again, Scott, are you coming in with a question?
Yeah, sorry to have another one.
No,
This
don't be
builds
sorry.
on-
Go ahead.
Sure.
You know,
Yeah.
we are
builds on
here.
John's interrogations.
Mm.
And, so, there's a couple cases, and I don't, if you have a chance to explore this further, I don't think the field, we understand this that well. So when you clip, there's a couple different cases. So one is you're clipping a specular highlight. And the specular highlight color basically is usually the illumination for most objects. Another case is you might clip and now you're clipping actual reflectance, like the classic is the white wedding dress kind of textures. So those are often called highlights in photography term, but they're not really specular highlights. It's more like white detail, or snow is, I guess, another example. So I'd be curious if you see different effects as you compare those. And then the third is what John was bringing up, where the brightest object in the scene is a chromatic, typically an illuminant object. And yeah, it's the computer graphics industry has done a lot of work in this area. If you clip it enough, you will definitely shift the colors.
Colors,
yeah.
you will
And
shift the shape,
there's
yeah.
actually many papers on trying to reconstruct highlights that are chromatically, basically chromatic emitters. So yeah, that might be. So anyway, there's kind of those three cases. And then it kind of ties in with, CIE colorimetry, where you're supposed to use the white reference, which isn't the maximum of the image. So the white reference is meant to be the maximum diffuse white region. So in a way, clipping the highlight, if you're clipping the specular or the chromatic illuminance, you're not affecting the white reference going into the CIE equations. So yeah, there's all those different cases, and it would be very interesting to see what happens, as you separate those out in the analysis.
Right. That's a really good question.
Right,
Actually,
yeah.
that's more detail in our analysis is how we calculate all those. We showing like a C-Lab, a QMH, and all those area. For example, for the first one, for the external one, when you do the clipping, we are assuming it's relative constant diffuse white. Actually, that matches with one of our presentation from it was in Paris. We did some work. Actually, the following work, as you said, is the diffuse white level estimation, with type of different processes. And when you have scaling and also the clipping, we give this experiment. We're showing that when you do the clipping, your perceptual or the diffuse white level does not change that much. It's more like stable. But when you do the scaling, it's almost like scaling as well. So which means, that's why how we use how we set the diffuse white in our computation is like for clipping, we use a constant one. Then for scaling, we use like a relative one. Yeah, it's as you say, actually, if the image itself is not already like as you said, it depends on the distribution. If the image itself is more like it's not a synthetic one, I would say mostly you will have some like a highlight area like that, but still that will just be a small portion of your image. Then when you do the clipping, as long as you don't go that really low, like 10 nits or like 100 nits, then you probably will have a really stable like diffuse light level, which means I would say at least from our experiments is showing in our processing, it should not change when you do the computation or either way. I think that we have that work is in Paris, it should be the year before. I think it should be 2019. I give a presentation there in CIC. Yep.
Okay, yeah, thanks.
Yep.
Great. So we should be wrapping up now, and thank again Fu to start with for his very interesting talk and very very convincing work, and a good start with Apple again, and congratulations for your PhD and for your award. Thanks those who threw in questions, and of course everyone who has attended. I remind you there are 2 more seminars, both on color this time during this series, and you will receive, if you haven't already, I think you have already received information on them, but reminders. So thanks everyone again, and I would like to close the seminar here. We can now stop the recording, and I'll see you next time.
Thanks everyone.